Hi everyone, my name is Satyaam Raha. Welcome back. So in the last video, we have already seen the concept of dropouts, which is a elegant concept, right? Now, after having seen the sigmoid function and the tanh activation function, let us see a different activation function which is used very popularly. Okay. Now, what was the problem with these activation functions, the sigmoid and tanh? The problem was vanishing gradient problem, right? So most of the values of the derivatives were so less, we had to run into vanishing gradient problem. Now, to solve that, a new activation function, which is most widely used, came into view. That is commonly known as ReLU, okay, rectified linear unit. So often it is used as the default activation function in many neural networks. Okay, so let us see with an example what is ReLU and how it works and why it is so famous till now. So let us see with an example. So I hope my screen is visible. So see, normally we have these values in our neural network. It could be in any layer of the neural network. Doesn't mean these x1 x2 should be the input layer. Okay, it could be at any hidden layer, doesn't matter. So let us say we have a neuron and let us say it is f. Now we'll have some w's over here, right, corresponding to the weights. Now at this particular position, before applying f, what we have? We basically have W transpose X, right? This W transpose X is actually put inside the function f, right? This function f could be any activation function. Till now we have seen two activation functions which are very simple yet problematic, right? The sigmoid and tanh. So now this W transpose X, let us say Z equals to W transpose X. Let us just suppose. Now what does ReLU say? So ReLU is an activation function which says f of Z is equal to Z plus. You can see it in the Wikipedia, you can refer to that. So what is Z plus? It is very simple. Max of 0, Z. It is as simple as that. If you want to visualize it, it will be like this. So f of z is equal to 0 if z is less than equals to 0 and it is equal to z otherwise. Okay. So this function f here is ReLU. ReLU. The full form is rectified linear unit. In short, ReLU. Okay. Most often it is also termed as rectifiers, just rectifiers. Okay. Now, how do you visualize it? How will it look like? So if I, okay, let me take a different page. If I say I have the axis, then how will it look like? If this is f of z and this is simply z and this is 0, then my ReLU function will look like a 45-degree angle, right? A linear line. This is basically 45-degree. So what is this? Any value, like whatever z is, f of z is directly that, if it is in a positive axis. Otherwise, it is simply equal to 0. It is as simple as that, right? You can see this. So if z is less than equal to 0, so the ReLU function will output as 0. Otherwise, if it is greater than 0, then obviously the value will be z itself. Okay. So this particular identity function, okay, it works like an identity function if z is positive. Otherwise, it will simply give a 0 result. I hope this is clear to visualize, right? Now the interesting thing is, what is the derivative of the ReLU function? So you see, if I plot here, if it is z, and if we have df dz, that is where f is a ReLU function, now it will be simply this. Okay, this is 1, this is 0. That means for all values which are positive, the derivative is equal to 1. It is constant. And anything, if z is less than or equal to 0, the derivative is also 0. Okay, now obviously there is a question that here we have a break, right? At this point what happens? At z equals to 0, what happens? For greater than equal to 1, we get it as 1, right? And less than 0, we get the derivative as 0. But at z equals to 0, ReLU is not differentiable. That is to be understood, right? Because we can see this is not smooth, right? From the concept of differentiation, we know that to differentiate a particular function, the function needs to be smooth, right? But here it is not smooth, right? It is kind of what should I say, a corner, right? So we cannot differentiate ReLU at z equals to 0. That is the problem. Yet this problem could be very easily overcome. Okay, that is not a problem. But the advantage here is, since this particular derivative of ReLU df dz lies between 0 and 1, like 0 and 1 can be the only values of the derivative. So there is an advantage. Also there is a disadvantage. Let me talk about it. So the advantage is we never run into the problem of vanishing gradient problem, right? Because the derivative could be either 1 or 0. So if we multiply in the chain rule, if we multiply multiple values, multiple derivatives, so what will we get? If we multiply multiple values, what will we get? We can get 1, right? Or 0. Now, so we do not get into the problem of vanishing gradients. Okay, that is, the gradients will not decrease, at least. It will not get to a very low value, right? So we won't face that problem, right? Also, we will not face the problem of exploding gradients, right? Because the values are constrained in 0 and 1. That is very powerful advantage, right? And the next problem is, since we have 0 also as the derivative, we can get 0 as the derivative. So what will happen? We could make this entire multiplication as 0, right? 1 0 could make the entire multiplication as 0. Now what will happen? As a result, we could have dead neurons problem. Okay, that is, the neurons will not update at all. Okay, in vanishing gradient, what we saw, it was converging very little, right? With very little speed. But here either will converge or will not converge, right? If one of these derivative is 0, right? So what will happen? This entire multiplication of the chain rule will be 0. Now what will happen as a result? As a result, the weights will not update, because as you remember, the formula was, if this was the formula for weights updation minus, this is old and this is new, minus eta times, we had this derivative, right? Let us say, like derivative of, let's take an example, like in the last example we took it as maybe dl by dw11, right? So this particular derivative could be a multiplication of many derivatives in the chain rule. So those derivatives might be 1 or 0 now, unlike sigmoid, unlike tan h, where we could have values lying between 0 and 1, right? But here we could have only 0 or 1, right? Now if that value is 0, then the entire entire value of this will be 0, then we'll have no updation at all. The old, this is nothing but the old w, and this is the new w, right? So the new w will be equals to the old w, so there is no updation at all. Now that is a rare case in case of ReLU, because we'll be using certain things called certain techniques in weight initialization, so we'll be able to avoid this problem much. But the advantage is we'll not get into the vanishing gradients problem. Okay, and ReLU, the derivative of ReLU is very easy, right? Either 0 or 1. So we do not need to calculate anything. Like you remember in sigmoid function or the tan h function, the derivative was a complex calculation, right? Complex term. But here it could be either 0 or 1. So a simple 0, 1 needs no calculation at all, right? So what will happen as a result? The calculation will be much faster. This derivative calculation will be much faster. Okay, so ReLU is widely used for that reason. Okay, that's it. Now there is a small change in the ReLU function. So what they did is, let me draw it in a different page. So we saw ReLU like this, right? ReLU was a 45-degree line. Here it would go to 0 directly, right? Now, since ReLU is not differentiable at z equals to 0, what they did is they made a smooth approximation, maybe like this, a smooth approximation of ReLU, and they called it as the softmax function. This is not very widely used, but it is in existence. Okay, softmax, my mistake. This is not softmax. This is soft plus. Okay, you can Google it. So soft plus. Now, what it looks like? It looks like this, and what the function looks like. So f of z is basically equals to log of 1 plus exp of z. Okay, I think it looks very similar, right? Similar to something. So let's see, what is the derivative of this? So derivative of soft max or soft plus is nothing but exp of z divided by 1 plus exp of z. Now do you find any similarity in this term? You can write it like this: 1 by 1 plus exp of minus z. Now do you remember this? This is nothing but the logistic function which you got in the logistic regression, right? So the derivative is nothing but a logistic function. So yes, that is why softmax was an approximation to ReLU. Okay, but yet ReLU is much faster, because this particular function, logistic function, is difficult to calculate than calculating the ReLU function. Okay, so that was it. Now the next thing is we'll have some modifications to ReLU. So one of them is soft plus, another one is noisy ReLU. Okay, you can Google it. It is not very much used. The Gaussian noise added to the ReLU. Okay, so it is not very much used. Next common one that is used very much is leaky ReLU. Okay, now before going into leaky ReLU, it is also a very simple concept. But before going into leaky ReLU, let me give you a problem or intuition why ReLU was a problem. Now see, let us say we have certain neurons going, certain edges going into the neuron. Okay, let us say this is x1, x2, x3 and all that, w1, w2, w3, all of those things, and this is f, let us say. Now x is obviously normalized. Before going into any of these layers, this x is always normalized. Okay, now what will happen if most of the w's are negative? What will happen if see, Z is nothing but W transpose X. Now, if most of the W's are negative, as a result, what will happen? Z will be negative. If W is negative, then obviously Z will be negative, right? And if Z is negative, you can see from the diagram here, from the diagram of ReLU, let's say this is the diagram of ReLU, right? So if Z is negative, the derivative is negative, right? So it will give you 0 as the result of the derivative, which means dead activations, right? So weights will not update anymore, right? That is why there was a introduction of a simple change in ReLU that is called the leaky ReLU. Okay, so how does it look like? Let us draw it. So this is same. Okay, this is 45-degree angle again. So this is nothing but Z. This is 0. And this is say function f of Z. This is for leaky ReLU. Okay, what they did is they simply multiplied a small term over here. This is not 0. This angle is not 45 degree. This is less than 45 degree. Okay, this is a very small angle. Okay, just not to make it 0, right? So what is the function? The function looks like this. F of Z is equal to Z if Z is greater than 0, right? It is identity. And it is, let's say, A into Z. Let us say A here is a constant term. A into Z otherwise. It is not 0 anymore. Like in ReLU, we had it 0. Okay, now what we are doing, we are multiplying a very small number. Let us say 0.0001, let's say. Now A is a very constant term and it is a hyperparameter actually when it comes to leaky ReLU. Okay, now what will happen? Will not have dead activations. Okay, the derivative of this particular thing df dz is nothing but, see, if we derive find a derivative of z is 1, right? And the derivative of az is nothing but a constant a, right? So 1 when z is greater than 0 and a when z is less than 0, right? Again there is a problem that this is not smooth, so it is not differentiable at z equals to 0. But yes, here we could avoid the problem of dead activations now, right? So A typically will be within the range 0 and 1, not 0. Okay, so that is how we could have many modifications of ReLU, but ReLU is the most widely used because ReLU is very much faster. Okay, because there is no problem of vanishing gradient and exploding gradient, and it is very easy to compute because the result will be only 0 or 1. That is the advantage. Okay, we do not need to calculate very complex functions like sigmoid or this tan h functions. Okay, but the only disadvantage you could say is dead activation. Yes, we can avoid it using the changes to ReLU, but this is the main concept. Okay, so I hope this entire concept is clear. If you have any doubt regarding ReLU or any variations of ReLU, what you could do is you could just comment it below and let me know. And if it is any way helpful, please do share it with your friends. Thank you for watching. I'll see you in the next video. Bye.